X.509 PKIs are systems built for the purpose of providing trust into the authenticity of cryptographic public keys. To construct this trust, X.509 PKIs themselves make use of various fundamental concepts from cryptography, and as such, we will start this course with a chapter covering the essentials of cryptography, which will allow us to later on then really understand the architectural design and the inner workings of X.509 PKIs. As fascinating as cryptography by itself would be as a subject for further investigation and analysis, for this course, cryptography is seen as a box full of tools with which, within digital information systems, the four classic security goals, confidentiality, integrity, authenticity, and non-repudiation can be constructed. Confidentiality is the security goal demanding that information in a system is only accessible to an authorized party. Integrity is the security goal demanding that the correctness and completeness of information can be verified. Authenticity as a security goal demands that in a system with authenticity, the source of information can always be verified by the receiving party. And non-repudiation as a security goal then demands that in a system with non-repudiation, the source of information can not only be verified by the receiving party, but that the source of information can be verified by any third party. Having now a first look into this toolbox that cryptography can be seen as, we find that cryptography approaches each security goal with one or more concepts and provides for each security goal clearly defined cryptographic primitives that can ultimately be used to construct the security goal within digital information systems. The primary cryptographic concept serving confidentiality is encryption, where some of the key primitives are, for example, the symmetric encryption block cipher AES or the asymmetric encryption scheme RSA. It's important to point out that this is an incomplete list with only just some very prominent example primitives listed, but with many more encryption primitives actually existing within cryptography. Integrity as a security goal is then served by cryptographic hash functions, where two of the most prominent primitives existing are the secure hash algorithm 2, SHA-2, and the secure hash algorithm 3, SHA-3. Two other prominent hash functions are message digest 5, MD5, and SHA-1, both of which I haven't included on this list though, as these two hash functions are not considered to be secure hash functions anymore for integrity-related purposes. Authenticity as a security goal is served by, for example, the concept of message authentication codes or authenticated encryption approaches. For message authentication code, a very prominent primitive is the hash-based message authentication code HMAC, and authenticated encryption is, for example, provided by the Galois Cantor block cipher mode of operation GCM. Non-repudiation as the strongest integrity-related security notion is served by cryptographic digital signatures, where two of the most popular primitives are the RSA-based cryptographic digital signature RSA PSS, or on the other hand, the elliptic curve-based digital signature system ED25519. To properly understand X.509 public key infrastructures, the concept of encryption, cryptographic hash functions, and digital signatures will be essential, so let's now have a closer look at each of these three concepts.